So in the last lecture we have discussed about the introduction to switch mode power converters, the valid phases and the different converter and the basic three DC-DC switch mode power converter topologies, that is buck boost and buck boost converters. So in this lecture we will discuss in detail about the operation and design of these DC-DC power converters. So let's first see buck converter. In a buck converter, this is the input source V in plus minus. In the buck converter, we have input side, we have a switch S1. As we have discussed, the other switch S2 we can replace with a diode, because the aim of that switch S2 is to operate in a complementary fashion with respect to S1, and its sole purpose is just to find a path for the inductor current not to be discontinuous. So that's why it is a first quadrant switch. A first quadrant switch means that a switch which can allow current flow in only one direction and which can oppose the voltage polarity of which can oppose voltage of only a single polarity. That's called as a first quadrant switch. So a power diode is the best example for that switch replacement S2. So we replaced S2 with a power diode. S1 is the power switch, which can be a powered transistor or a MOSFET or IGBT and so on. Then we have an inductor. This is IL1. Say this current is ID. This current is input current. The voltage across the switch is VS1 and this is IS1, current through the switch. After this we have the capacitor and then the load. So this is V0, this is V in, and this is I load. This is a capacitor, this is the capacitor current IC. So this is a buck converter. So before we see the operation of these converters, we'll first understand what are the states of this converter. A state means quantity which cannot suddenly change, or whose dynamics are governed, or the dynamics of the whole system can be governed by controlling the or by knowing the response of these states. State means a quantity which does not vary instantaneously. So as you know that in an inductor, the inductor current cannot change instantaneously. So in the inductor, the state is the capacitor current, inductor current. It's a state. Similarly, for a capacitor, the voltage across it is a state. We know that voltage across inductor is L DIL by dt, and current is ICC dVc by dt. So whenever there is a change of current, then only the voltage so as the current across the current through inductor changes, that will govern the voltage drop across it. Similarly, vice versa for the capacitor. So these are the two states. Now we know that an inductor stores its energy in the electromagnetic field, and the capacitor stores energy in it in the form of electrostatic energy. So in this inductor we have lines of flux, that is electromagnetic, and a capacitor stores energy in the form of electrostatic energy storage. So if we see how does an inductor and capacitor behaves, is that, so what happens is, if you excite an inductor by a voltage supply, then some voltage is applied across the inductor, thus a current will try to flow through it. So based on the load requirement and based on any change in the circuit, the current of the circuit will change, and thus an inductor will not allow sudden change in the its current. So it will have some lag before the change in the current. The expected change of current, let's say it is from IL1 to IL2. So the inductor will not allow sudden change in it. It will be governed by this inductance, and it will govern by the voltage drop across this inductor. So if we write IL is 1 by L integral VL of dt plus IL of 0. Similarly, Vc of t, this is IL of t, Vc of t is 1 by C integral Ic of t dt plus Vc naught, the initial value. This is an indefinite integral. So the energy across inductor is half Li square, and the energy across the capacitor is half CV square. So let's say that the power converter, the switch S1 is operating using pulse width modulation, means pulse width modulation scheme, which means that it operates as an on-off state. So which means that a carrier signal, say this is a D, or called as a carrier signal. Say this is a ramp signal having some frequency, switching frequency. So if we compare this so these are the pulses, switching pulses of S1. So this is the carrier C. So how we write it is that if D is greater than equals to C, then S1 equals to 1, else S1 equals to 0. This is a modulation scheme, pulse width modulation. Means you are modulating the width of the pulse based on the instantaneous comparison of the carrier signal with this is not carrier, modulating signal with respect to carrier signal. This is a modulating signal. Similarly, the carrier C can be sawtooth. So this waveform carrier is called a sawtooth, or it can be triangular, which means that like this, where this is the switching frequency. So in switching power converters, as based on the position, so this particular power converter is highly discontinuous in nature, because when the switch is on, the circuit connection is somewhat different, and when the switch is off, the circuit connection is somewhat different, which means that it is a very discontinuous in nature. And we have to analyze the states of the system. Here it's a second order system because it has two energy storing elements. So the states are the inductor current and the capacitor, or the output voltage. So we have to analyze this circuit with respect to the switching. So let's say if the switch is turned on, so what happens is now the inductor is connected between output and input. So the voltage across inductor is V in minus V naught. So let's assume that it's a buck converter. So our assumption is the converter should do bucking action, means V naught should be less than V in. This is our assumption. Okay. So when the switch is on, the voltage across inductor is V in minus V naught, and the diode is reverse bias. When the switch is off, the diode D becomes forward bias, because the inductor current is equals to the diode current ID, which will force the diode to turn on. In that case, the voltage across, let's say this is the voltage across diode VL, this is plus, this is minus. So if the switch is S1 is off, D is forward bias, means it's short circuit. So the voltage across the inductor is minus V naught. So minus V naught. So voltage across inductor is of this nature. So let's draw all the waveforms, and now I am drawing all the waveforms of the power converter. First is I'll start with the gate pulse. I'll draw only 2 cycles. So these are the gate pulses for S1. This is 1, this is 0, 1, 0. Again, this is D into T switching, and this is F switching. Okay. So I have drawn here 3 cycles, 3 switching cycles. Instead of 3, you can call 2.5 because the third is just for on time. So when the switch is on, we'll first see the states, how the states will behave. So we'll see the voltage across the inductor VL. This is S1, this is VL. So VL will be this value will be what? V in minus V naught, and when it is off, it is minus V naught. This is minus V naught. This is VL. So as we know, so for the first half cycle, for the plus half cycle, if the voltage across inductor is positive, which means that the current through it will, how will be the nature of the current? It will be the integration of voltage. Okay, it will be integration of voltage. So let's assume that there is some initial current IL naught, which is some positive value. So let's say if you want to draw IL, or we'll draw IL here only with some other color. So let's say this is IL naught. So it will start rising, this current will start rising with a constant DC slope. Okay, then when the voltage polarity across the inductor is not negative, which means that the voltage has changed, reversed its polarity, which means that then IL naught will be minus slope because integration of minus V naught. So it means that as the polarity has reversed, the current should fall. So the current is falling. We don't know what are these values of current here and here. Again, when the next cycle is turned on, then this will rise, again it will fall, again it will rise, and again it will fall. Now we don't know these values. Say we don't know this value. So let's say we know this value. This is IL naught. This is what? IL at what time? T switching. This is IL at D into T switching. And again this will be IL of 2 into T switching. This will be again IL of 2D into T switching. Okay, so we don't know what should be the values of this inductor current peaks. Now say that at the end of each cycle, let's say the values IL of T switching, we have 2 sets of values. One is the value of the inductor current at the end of the cycle, and the other one is the value of the inductor current at the end of the on cycle. That is, we have, instead of writing like this, I'll write IL of at N into T switching, and we have IL of N into D into T switching. Okay, so if we make sure that IL of D into T switching equals to IL of 2D into T switching equals to IL of N into D T switching equals to some IL max, which is known value IL max, and IL of T switching equals to capital IL of 2 into T switching equals to so on till IL of M into T switching equals to some IL minimum. So what happens is, now the inductor current will be bounded between two values. So let's say IL naught, we will consider it separately. So what happens is, let's say this is IL naught, it will rise, fall, again rise, fall, rise, fall. So this is IL max and this is IL min, and we can call this as delta IL. This is the delta IL. This is IL waveform. This is IL of 0 and the average value of it. This is capital IL or average of IL. This is the average value of the inductor current. So if you make sure that the value of the inductor current at all on times is equal to some IL max and and the value of the inductor current at all end of the each switching cycle is equals to IL minimum, then we'll find that the average value of inductor is almost constant, which is desirable. Why? Because let's assume that so we say that IL should be constant since IL load is constant. Now why IL load is constant? Since V naught is constant. Now why V naught is constant? Since C naught is very big. C naught is very big. So bigger the capacitance, less will be the peak ripples in it. Okay. Less will be the peak ripples in it. So now we analyze that. Now we'll see the capacitor part later. First, we found that this also means that if the value of the inductor current at the end of all on times is equal, similarly at all off times or at the end of each switching cycle, if they are equal, which means that the value of inductor current is constant, and this means that during the on time the inductor is energized and the off time the inductor is de-energized, and the rate of energization is equal to the rate of de-energization. This should happen. Why? Because if the energization and de-energization of the core is unequal, then the inductor will be building up its flux. So what will happen is, this will happen, which is saturate the core, which means that now the inductor will not behave like an inductor. So in these two cases, IL max and IL min are not equal. So we do not want that. If the core is saturated, it means that the inductor will behave just like a short circuit. It will lose its inductance properties. So that's why the rate of change of energization and de-energization of inductor should be constant. Now what does it mean? If you see this expression, IL is integration, this expression IL is 1 by L integral of VL of dt plus IL, which means that, so integral of VL of dt means this is area under the VL versus time graph, which means that if the average, this is the average value of inductor, let's say that the average value of inductor current is always constant, which is equals to capital IL. So it means that in each switching cycle, the average value of VL of t. So which means that integral VL of t dt 1 by L integral 0 to say t should tends to 0. Instead of t, we write t switching. So if you break it into two parts, what we'll get is integral 0 to t into t switching into VL during on time of dt plus integral of d into t switching till t switching VL of dt should be 0. If we substitute, what we'll get is integral 0 of d into t switching. What is VL on? When the switch is on, the voltage across the inductor is V in minus V naught. So here I will write V in minus V naught. Both are constant. Let's assume that V in is constant, it is not changing, and the V naught is also constant because the capacitor output capacitance is very high. So the average value of the capacitor voltage is almost constant of dt plus integral d into t switching till t switching. It is VL of, it is minus V naught of dt equals to 0. If we write it, it will be V in minus V naught into t. If we substitute t, it will be d into t switching minus V naught into t switching minus d switching is 1 minus d into t switching equals to 0. If we cancel out t switching, we'll get V in minus V naught. If we send this to right hand side, it will be V naught into 1 minus t. Sending V naught to this side, it will be V naught equals to V naught of it will be minus of V naught. So in this case it will be d into V naught. So d into V in will be, if we take V naught common, it will be V naught into 1 minus d plus t. It will be cancelled. So V naught will be d into V in. This is the steady state relation between the output and input voltage for a DC-DC buck converter. So this can also be written as, or this can also be written as VL during on time into T on time. Why? Because it is integrated from 0 to T on, plus VL during off time into T off. What is T off? T off is T switching minus T on into T off equals to 0. This we can write as sigma VL I into Ti will be 0, where I equals to 1 to n. So basically, if we have two switching, that is, so if in one switching period we have two types of switching, on and off, then I equals to 2. That is, we'll have T1 and T2, where T1 is T on and T2 is T off. Let's say there is a third state in it, so it will be I equals to 3. So VL1 into T1 plus VL2 into T2 plus VL3 into T3 equals to 0. So which means that the inductor core is not saturated, and this is with all the assumption that V naught is constant. Now we'll see with the waveforms what will be the nature of the other quantities. Now we'll see Vd plus minus. We'll draw Vd and Id together. So, and Vs1 also we can draw together. So if we draw, so Vs1, if the switch is on, the voltage across it is 0. So, and if the switch is off, the voltage across it is if the switch is off, the diode will be, if the switch is off, the diode will be what? Forward bias. Forward bias means it will be short circuited. So voltage across the switch will be V in, plus of V in. So this is 0, this is V in. Okay, this is V voltage across the switch Vs1. How will be the current? If the switch is on, the diode will be for reverse bias. So the current Is1 will equal to the inductor current, and when the switch is off, the Is1 will be 0. In that case, the inductor current becomes the diode current. So in the so when the switch is on, this is Is1. So this will be what? IL1 max. This point will be Is1 min. So this for the switch, the voltage and currents are done. Now for the diode, we'll draw for the diode. Voltage across the diode. So voltage across the diode will be of the reverse polarity of that of the switch, but with different values during the off states. When the switch is on, then the voltage across the diode is V in, and when the switch is off, the voltage across the diode is 0. So it will be from V in to 0. So it will be like this. This waveform is Vd. This value is V in. This is 0. Now the current through the diode, when the diode is off, the current in it will be 0. When the diode is on, the current in it will be the inductor current. But this is valid only for off time. So if we draw here, it will be like this, falling slope. This will be IL min. This will be IL max, and this waveform belongs to ID, the diode current. So what we saw is that the inductor current is basically split into two waveforms. The waveform during the on time are shifted towards the switch current, and the waveform and the current waveform of the inductor during the off time is shifted as the diode current. So that is an observation. Now we'll see, now in input side all the circuit elements, voltage and current waveforms are done, and similarly In equals to Is1. So in the waveform of Is1, this will be In. Is1 is equals to In. So we have drawn all the waveforms. Now we'll go to the output side. Okay, let's assume that I load is constant, like this. Okay, so this is, let's say we have a V0 by capital R. This is I load current. So No need to draw iload again. So what we'll do is, using the KVL here, KCL here, IL equals to IC plus iload. So IC is IL1 minus iload. Okay. IC will be IL minus iload. The waveform of IL is a triangular waveform with the average value. Okay. If we draw like this, this is the average value. This is capital IL, average value. So from this waveform we are subtracting some constant waveform, which means that the waveform of IL we are shifting it down. So IL waveform will be like this. This will be the peak value of it is now changed to IL max minus iload. Say V0 by R I am writing, and this value will be what? IL min minus V0 by R, because the whole waveform is shifted down, and this is the average value. So this average value is what? Average value, capital IC is what? Some capital IC, we don't know. And this waveform belongs to, this is the t equals to 0 axis for the waveform. This waveform is of IC of t. Now we don't know what is the average value of the capacitor current. We don't know what is the peak values of IC. So IC max minus V0 by R is IC max. This we can write as IC max, and this we can write as IC min. Now we don't know IC max, IC min and capital IC. So if we apply the same energy storage principle of the inductor of the capacitor, the only thing is capacitor stores energy in electrostatic form. So for the capacitor not to saturate, in this case, if the inductor saturates, it will lose its inductance properties. It will be a simple short circuit. Means it will not store energy and release energy, store and release energy for each switching cycles. And the average value of inductor will not be constant. It have different rates of energization and de-energization. So similarly, the energy storage principle will apply on the capacitor. So the energy in one cycle, let's assume that the capacitor is energized, and the other cycle the capacitor is de-energized. Energized means by somehow the capacitor is connected to the input voltage source V in. In this case, in which phase does the capacitor gets the energy energized? It happens when the switch is on. If the switch is on, there is an inductor between the V out and V in, which means that from the source the current I in flows through the inductor, and then it goes to the diode. So let me also draw during for on time. The circuit will look somewhat like this. It will be short circuited. Switch is placed here. Yes. This will be open circuited. Then there will be a diode. There will be a switch, and there will be a load. So this is VD. This is L. This is IL. This is IC, and this is I load. V in, I in, and IS1. During off time, the circuit looks like this. This is open circuited, and this is short circuited. In this case, the inductor current will force the diode to be forward bias, and ID equals to IL. VL. Okay, this is V0, this is V in. Okay, the I in this case will be 0, and this is the VS will be V in, and IS1 will be 0. So in the on time, the input gets connected to the output via the inductor. The inductor will be charged. If the inductor is charged, why the inductor will charge? If the voltage polarity across the inductor applied voltage is positive. As we know that the assumption is V0 is less than V in, the voltage across the inductor during on time is positive. Why? Because it is V in minus V0. Now then the inductor current will start rising with a linear slope. The slope is given by this expression, delta L by delta T. So the slope will be given by VL by L, and VL is V in minus V0 by L. So you can also write like this. This is IL. So this slope equals to V in VL on by L, and this falling slope is given by VL off by L. This is the average value of the inductor current. This is IL max, this is IL min, and this whole thing is the peak to peak ripple, that is delta IL, peak to peak ripple. So during the on time the capacitor is energized, and during the off time the capacitor is de-energized. Why de-energized? Because now the input, because now there is no active supply. So whatever is the load demand, that has to be primarily or momentarily given by the capacitor. So during, as we know that energy storage principle, the capacitor should energize and de-energize with the same rate, half CV square. So which means that this expression should be valid, that is Vc of t. What is Vc of t? It is V0. Our assumption is that V0 will be almost constant with some switching components. Okay, it will have some switching components. So first we'll see the waveform of IL, because if you want to, we can't draw both together. We'll first draw the waveform of IC because it is easy to draw. IC is what? IL minus iLoad. iLoad is constant. There has to be one assumption. Assume that it is a linear and constant load. So IC waveform is the waveform of IL pushed downwards by the rate of V0 by R, or by the rate of the load current. Now we have to make sure that as per this expression, Vc of t is 1 by c integral IC of t dt plus Vc of 0, which means that, say similarly, this is the area under the IC versus time graph. So similarly, let's say that this has to be 0. This is again area. This is again area versus the area of IC versus time graph during different instances. So let's say this is the equals to 0 axis for it. Okay, so which says that during, so using the volt second balance, so the thing which we derived here for inductor, where is it? It is this one. This is called as volt second balance for the inductor, that is multiplication of volt into time seconds, summation of them equals to 0. So similarly for capacitor, we have amp second balance. So the amp second balance is sigma IC of I into Ti equals to 0, where I equals to 1 to n. So which means that IC on into D, or we can write T on plus IC off into T off equals to 0. which means that the area under IC versus T graph is equal for charging as well as discharging phase. Let's see what is the area and how the waveform is. Now what I have drawn is that I have shifted the waveform of IL downwards, but it still has some average value. For volt second balance, VL on into TL on plus VL off into L off is 0, which means that the area under VL versus time graph are equal for charging and discharging phase, which means that the average value of the inductor current, during the whole T switching will be 0. Similarly, the average value of the capacitor current waveform during the whole switching time should be 0. Similarly, for the amp second balance, if the amp second balance is lost, then the voltage across the capacitor will keep on changing. It will be either rising or falling. That is not desirable. So for using the same amp second balance, we have to make sure that the area of this curve has to be equal for charging as well as discharging phase. Now in this case, I have not, this is the T equals to 0 axis, and this is the area during some switching, and this is some area during some other switching time. So as I said, in the capacitor current, so this is the T equals to 0 axis. For this is the inductor voltage waveform. So this is A1, this is A2, which means that A1 equals to A2 using this principle. Where I have written here. So A1 equals to A2 for inductor using volt second balance. Similarly, A3 equals to A4 for capacitor using amp second balance, or you can write current second balance. So what is A3, A4? This should be A3, A4. But so if A1 equals to A2, which means that A1 is positive area and A2 is negative area. Why? Because it is below the T equals to 0 axis. But in this case, A3 and A4 both are above the T equals to 0 axis, which means that the proportion by which we are shifting the IL waveform downward is insufficient. We have to have some negative area or some area going below the T equals to 0 axis. But in this case, T equals to 0 axis is further. So let's assume that we shift it further down, and I erase this axis. And I make this axis as T equals to 0 axis. This one. This is T equals to 0 axis. Okay. This is T equals to 0 axis. Now I'll derive A3 and A4. This was D into T switching, and this is 1 minus D into T switching. This is a 0 crossing, this is a 0 crossing, this is a 0 crossing, and this is 0 crossing. So by this configuration, it is slightly difficult to find A3 and A4 and to equate A3 and A4. So what we'll do is, inside one switching cycle, we'll take some other switching cycle which is easy to find. So we have to see so these zero crossings are not aligned with the turn on and turn off instances. So we can shift the A3 and A4. So what we'll do is we'll shift it. So this is 0 crossing, this is 0 crossing. Okay, so what we'll do is we'll say this is the new A3 and this is the new A4. Similarly, or we can write this is the new A3 and this is the new A4. This also we can write. A3 and A4 in all the cases are triangles. So we have to, area of triangle is half into base into height. Okay. So by deriving this, we can derive the the ratio by which we have to shift down the IL waveform so that A3 and A4 will be balanced. That we'll get by solving A3 equals to A4. Okay. And say this is the slope. This is the slope. What is the slope of the falling edge of the inductor current? It is mentioned here, VL off by L. VL on is V in minus V naught by L. This slope is minus V naught by L. The slope is minus V naught by L. So this will happen. So now our aim is to find by this area and equate this area A3 A4. By the equating A3 A4, what we will get is that by how much proportion we have to shift the inductor current waveform, so that we'll get the new capacitor current waveform, so that the amp second balance is satisfied by for the capacitor. Why? Because the voltage across the capacitor should be maintained constant. So if we map the zero crossing points over the original inductor current waveform, it is somewhere here. Okay, it is somewhere here on this edge, and there is this waveform has some average value. Okay, this waveform like this, apart from these ripples, it has some average value. Now by looking at this, you can say that this waveform may also have some average value. It has some average value. This is delta IC. So delta IC will be equals to delta IL. Why? Because delta will be same. Will be delta IL. And we don't know what is the average value of this waveform. But we know that with the same principle, the average value of the inductor voltage across inductor should be 0. Then only we can say that area A1 equals to A2. Similarly, as now it's slightly difficult to equate A3 and A4 because we don't know at what point the zero crossing is happening. Even if we map the point to the original inductor current waveform, we can go the reverse fashion. So in this fashion, we say that A3 equals to A4, which means that the average value of the capacitor current is 0. With the same logic, because average value of inductor current in each cycle will be 0, then only the inductor will be equally charged and discharged. So average value of VL for a T switching should be equals to average value of capacitor current for each T switching should be 0. Then A3 equals to A4. So the average, we know that the average value of inductor current is this. This is the average value, capital IL. So if we shift the waveform of inductor current by the proportion of its average value, such that the average value is 0. So average value will be 0. So IC should be 0. In that case, what we will know is that this is exactly midpoint. This is exactly midpoint. Why? Because the average value we are making it as 0. So the zero crossing is exactly happen at the midpoint of this slope, this curve. Then it becomes slightly easy to find the areas. Now as this point is midpoint of these 2 points, average of these 2 points, and at this point is average of these 2 points, what we can do is, if this is one switching cycle, then this is half of it and this is half of it. What will be this? This will be D into T switching. Similarly, from here to here, or if I avoid the confusion, or I'll erase this. Now I'll draw it. Let's say my reference point is the zero crossing point. What is one switching cycle next to this point? It is this point. Okay, so this point to this point is a one switching period. Okay, this is the switching period. In this switching period, this waveform is a midpoint of it. So this will be exactly T switching by 2. So from the symmetry we'll get to know that this point to this point is T switching by 2, which means that IC will be 0. IC will be 0. The average value of IC, not just the IC instantaneous, the average value of IC. The average value of the capacitor current should be 0. Okay, so it will make sure that capital IC will be 0. So now what happens is, this is the circuit configuration. This is the inductor. If you draw only the output side, and this is the load. The load current is like this, I load. This is I load, and this is the inductor current, IL. Then the capacitor current will be what? It is of only ripple nature with 0 average value, which means that, and this holds true, IL is IC plus I load. It means that inductor current which has a ripple plus an average value, what happens is the average value goes to the load, and the only ripple which is the remaining part goes to the capacitor, which means that IL equals to I load. Is correct? And capital IC should be 0 with 0 average value. So this you will get using the amp second. This you will get using the amp second balance. Why? How will you get this? Is because you are shifting the waveform of inductor current down in such a way that its average value is 0, which means that you have completely removed the average value from the inductor current, and then the whole average value has to go to the load. That's why capital L equals to I load, which is from the amp second balance. Using the volt second balance, you can get the relation between input and output voltage, which is V0 is dV in, and capital IL is I load. Volt second balance, and this is amp second balance. So V is V0 equals to dV in is by ideal conditions. So what are the typical non-idealities? In the source we have a equivalent series resistor. For inductor we have the resistor and the interturn capacitance. So this will become RLC. As the interturn capacitance is very small, it can be neglected. So the inductor has inherent equivalent series resistor. Similarly, for a capacitor, it has a ESR. For a diode, it has a how does a diode behave during off time? It is a 0 open circuit. So during off time, it is like this. This is VDD. This is VD. Drop across the diode plus minus. This is VDD and this is RD. This is ID. So during the on time we have considered the diode as ideal. So that is completely during off. When the diode is on, it is completely off. There is no ESR or VDD. So this is the non-idealities. So by avoiding all the non-idealities, we'll get V0 equals to dV in for a volt second balance. So if we plot the relation, let's say m of t equals to d, that is V0 by V in, or the slope. So if we plot like this, it will be d, and this is m of t, which is a linear slope. This is 0 to 1, which is the maximum value for the buck converter. For 0.5, again linearity, it's a linear. This is 0.5, m is also 0.5, it is a linear. So now we have seen the operation of a buck converter. Okay, operation of the buck converter. In the next lecture, we'll see how to design the different, or how to select the different components of a buck converter, like what should be the rating of the input voltage, the switch, the voltage current rating, the diode rating, the inductor, how to design the inductor, the capacitor as per the load. That we'll see in the next lecture. So in this lecture we saw how the buck converter behaves. So before starting the analysis of the buck converter, we assume that the load current is a constant current, the output capacity is very high, such that the output voltage is almost constant, or the average value of output voltage is almost constant. So I think we forgot to draw the waveform of the output voltage. So the output relation. So now we have the waveform of the capacitor current. Now we can easily draw the waveform of the output voltage. What is V0? V0 is, or Vc is 1 by c integral of Ic of t dt. This is the integration of it, and this is a linear curve, that y equals to mx plus c wala curve. If you integrate y equals to mx, we'll get x square by 2, so it will be a quadratic. So this is t. So during the on time, it will be a polynomial type of thing like this, and then again the slope is falling, which means that it is be a reverse polynomial, like this, again like this, again like this. So this is V0. So it is V0 max, it is V0 min. Our assumption is that V0 max, all are V0 max and all the V0 minimum should be constant. So between V0 max and V0 min, the waveform of the output voltage will vary, and this is the average value, that is average value of V0. So V0 max you can easily find. V0 is what? Ic max by c and V0 min equals to Ic min by c. Why? Because we are integrating it, and again the peak value will be this thing, 0 to t switching. Yeah, so you can get it. So we saw that the average value of the inductor current should be constant. Average value of the voltage across inductor in each cycle means the average value of inductor voltage should be 0, which means that it should energize and de-energize equally, or the areas A1 and A2 in the inductor voltage versus time graphs should be equal, positive and negative. Same thing with capacitor. Average value of capacitor current should be 0 to maintain its output voltage as constant. If the average value of capacitor current is not 0, the average value of the capacitor voltage will keep on rising or falling. And the areas between the IC versus time graph during the positive and negative areas during the turn on and turn off time should be equal. So this is the amp second balance. So these are the steady state waveforms, not the transient waveforms, not the turn on waveform, change in load or changing input voltage or changing or addition of any disturbance. These are just transient waveforms of the buck converter with respect to the switching pulses S1. And we have derived some volt second balance using some integration and areas, and with some assumption of we first started with the assumption of the energy storage in the capacitor and inductor. Accordingly derived the volt second and amp second balance, and then derive all the expression of this thing, and then finally derive the steady state voltage gain of the buck converter. Voltage gain means the ratio of V0 versus Vin. In the next lecture, we'll see how to design the switches and the other converters. So this particular buck converter took a lot of time to draw the waveforms. In the next boost and buck boost converter will take less time, because I hope now you understood how to draw the waveforms by different assumptions. So I won't make it repetitive. So those analysis of those converters will be quicker than buck converter. That's why we stopped here. Some of the portion of buck converter is still remaining, that we'll see in the next lectures. Thank you.